Complex number part 2. And so what we're going to be talking about today is the Argan diagram. Then we're going to be looking at locus. We're going to be looking at Argan diagram, locus. We're going to look at polar form and the Marvelous Theorem. Those are what we're going to be doing this week. So what is the Argan diagram? So you know that typically when you get maybe functions and relations, you have graphs to plot. Now with complex numbers, the same way we're going to be plotting what is now known as an Argan diagram for a complex number. All right, so for real numbers, we plot graphs. For complex numbers, we plot what is known as an Argan diagram. So how do we do this now? So let's say we have a complex number z. We have a complex number z, and if we have a complex number, z is equal to 3 plus 4i. 3 plus 4i. What they say is that this complex number, we can put it on an Argan diagram. What is the real part of this complex number?
3.
3. And what's the imaginary part?
4.
4. Nice. So what we can then do is they say that we drawing the Argan diagram for a complex number, there are two axes. The x-axis is known as the real axis. And so oftentimes you're going to see RE of z. This means the real axis of z. So you'll say REZ. And then up here, you'll say IM of z. And this means the imaginary axis. Imaginary axis, IM. Imaginary axis for the complex number z. And I'm still writing real poor because of my finger. Alright, so yeah. So now what we say is to draw this complex number on the Argan diagram, 3 plus 4i, is the real part is 3. So the real part is 3, and the imaginary part is 4. So we plot it as a point. So we look for the point 3, 4, and then we draw a line from the origin to that point. And so this would represent the complex number z, where z is equal to 3 plus 4i. So here we have the notes, and it says a complex number is represented in triangular or Cartesian axis. An Argan diagram is just a plot of the complex number as a point in the complex plane, the horizontal axis or the x-axis. This is the axis that we use to plot the real values of z, and on the vertical axis, we plot the imaginary part of z. All right, so they say let z equal x plus yi. Then a point can be used to represent the complex number as z is equal to the vector OP, which have coordinates x, y. So this is a complex number in vector form. So we can write also this complex number in vector form. And so this complex number z is equal to, in vector form, it would be 3, 4. And we can also write it in coordinate form as a point. And as a point, it would just be z is 3, 4. This is in coordinate form, 3, 4. All right. And that's all there is to the Argan diagram. All right. So a complex number can be represented as z is equal to x plus yi. This is the Cartesian form of a complex number. So far we've been looking at most of the Cartesian or the standard form of a complex number. All right, and we're going to learn about different forms that we can express the complex number in. All right, so here's just a typical diagram expressing, to just represent This is just a visual representation of the Argan diagram. The imaginary axis, or you'll see the imaginary part of Z, the real part of Z, and this is then the point right here. The point is right here, and there's always going to be an angle. There's always going to be an angle from between the x-axis and the line. All right, so if we go back up here, when we draw this complex number 3 plus 4i, you notice that there is always going to be an angle between the positive x-axis and the line. Now the angle between the positive x-axis and the complex number line, all right, now this angle that we're going to learn that they call it this is the angle. All right, so the angle that we're always going to be looking for in complex number is the angle between the positive x-axis and the vector itself, this vector. All right, so now let's look at a few to sketch for the Argan diagram. It's pretty simple. All right, so let's look at a few. So let's say we're going to show these complex number on an Argan diagram. So 3 plus I, 4 plus I, all of these. Let's show all of these on an Argan diagram. All right. All right, so help me now. We're going to sketch these on an Argan diagram. So the first one is we have the complex number 3 plus I, then 1 minus I, then 4 plus 2I, then minus 1 minus I, then minus 1 plus I. So let's sketch these on an Argan diagram. All right, so the first one we have 3 plus I. Oh, we're going to sketch the one 3 plus I.
We're going to make 3 be on the y-axis, the positive y-axis.
The 3 is going to go on the positive y-axis, you sure? This is which part? The 3 is what?
The 3 is the real section.
The real part. So the real part goes on the positive x-axis.
Okay.
Right,
and
so
then the imaginary part go on the y.
Yes. Okay. And the imaginary part go on the y. So we can put our 3 right here. And then we have positive 1, so we can put 1 right here. This is the imaginary part of z. And so we have the point 3, 1. So the point 3, 1, like that. That's a complex number. There it is. And you can express it as a point as 3, 1. The real number for the x part, the imaginary number for the y coordinate. All right, and that's a complex number 3 plus I. All right. Now let's look at the complex number 1 minus I. Talk to me now, 1 minus I.
So 1 would be on the x-axis.
1 would be on the x-axis, all right.
And then that would be negative 1. So
very good, negative 1. Negative 1 on the y-axis, very good. Negative 1 goes on the y-axis. All right, so the point is going to be 1, negative 1. And then we always draw the line from the origin. So we're drawing a line from the origin to 1, negative 1. All right. Now the angle that we're talking about is always the angle between the positive x-axis and the line. And so this would be the angle that would be in consideration. All right? This angle right here. All right, so this is the complex number. And again, always label it as our real part and our imaginary part of that complex number. All right. I'm just going to put 4 plus 2i on the same diagram up here. How would we draw 4 plus 2i?
4 would be on the positive x-axis and 2 would be on the positive y-axis.
The 2 on the positive, very good. And so in red, you have the point 4, 2, and that would represent, then you just draw a line from the origin to 4, 2, and that would just represent 4 plus 2i. All right, very good. Now let's just look at one last one. Minus 1 minus I. Minus 1 minus I. Talk to me.
Negative 1 would be on the negative part of the x-axis. And
very good.
The negative 1 would be on the negative part of the y-axis.
Very good. Negative 1. All right. And then again, we always draw from the origin to the point. All right. So we label the point and we draw from the origin to that point. And then we leave it like that. All right. So that's it for really drawing Argan diagram. And the Argan diagram is just a build-up of many more things that we're going to learn. All right. So always just label the axis when we're finished, the imaginary part and the real part. All right. All right. Now let's go to something new now. That takes care of Argan diagram. The next thing now is what is known as the modulus, or the length of a complex number. The modulus or the length of a complex number. So consider a complex number z equal to x plus yi in Cartesian form. All right, this is a complex number in a form that we're used to. Now, they say that let r be equal to the square root of x squared plus y squared. R is called the modulus of z and is denoted by mod z. All right, and they call r the modulus or the length of the complex number. So every complex number has a length. How do we now find this length? All right, how do we find this length? Now, if you were to look at a complex number, z is equal to x plus yi, right? Then on the x-axis, the length from the origin to right here would be a length of x. The length on the y-axis would be from here to here, which is y, right? So the length to here is y, all right? So this distance between here is y, this distance is x. Now we know from trigonometry, since there's an angle right here, and this makes a right angle triangle, then we're going to know that r squared, where r squared is the length of the complex number, r squared is going to equal to x squared plus y squared by Pythagoras theorem, right? R squared is going to be equal to x squared plus y squared. That's just Pythagoras theorem. R squared is x squared plus y squared. And so if we square root everything now, that will then be able to give us what is r. So if we square root this now, we get that r is going to be equal to the square root of x squared plus y squared. And that's the length of a complex number. That's how we find the length of a complex number. All right, so let's look at an example. So a simple example would be, let's say z is equal to 3 plus 4i. Z is equal to 3 plus 4i. If z is equal to 3 plus 4i, we know that the real part is 3, the imaginary part is 4. And so if we were to draw the Argan diagram of 3 plus 4i, we have the real part of 3 and the imaginary part of 4. And so when we plot the point 3, 4, right? Now this part is going to give us the length of the complex number, this right here. Now the length of this complex number, if we draw a broken line or dotted line go down, we get that the y value for here is 4. The y value is 4. And the x, or the length on the x-axis, is 3. And so what is going to be now, what's going to be the modulus or the length of this complex number? What's going to be the length of this complex number? As they'd call it, R.
Would it be 5?
Yes, it would be 5. How did you get the 5?
3 squared, square root of 3 squared plus 4 squared.
Very good. So that's how we would find R. So we'd say R, and you don't have to write R, you can call it the modulus of Z. So R is just the square root of x squared plus y squared, which is just the square root of 3 squared plus 4 squared. And when we square root 3 squared plus 4 squared, we're getting, as you rightfully said, 5. And so the length of this line is 5. All right, and that's how we can find the length of a complex number. Nice. So here are 2 examples that we're going to do. We're going to find the modulus of the following. So let's find the modulus of this complex number. So for part A, we have z. We have that z is equal to 2 plus I. So it will be the length of this complex number.
It'd be the square root of 2 squared plus 1 squared.
Very good. Very, very, very good. It will be the square root of 2 squared plus 1 squared, which is just the root of 5, right?
Yes, sir.
Nice. So let's leave it as the root of 5. Now let's challenge you a little bit. Look at the second one now. Ta 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 ta. What's the modulus of the second one? We have 2 minus I.
So it'd be the square root of 2 squared minus 1 squared. So it'd be the square root of 3.
Oh, you get 2 squared minus 1 squared. It's going to be
because it'd be the same thing, right?
the same
so it'd
thing.
be square root of 5.
Yes, it's going to be the square root of 2 squared plus 2 squared plus minus 1 squared. Because the y value is just minus 1, right? Minus 1 squared. When we square root it, we just get the root of 5. And let's look why both of them have the same length. Now, if you were to draw them on an Argan diagram, how would 2 plus I look?
2 would be on the positive x side and I would be on y.
Very good.
Y.
Nice, which is 1. So let's say this is the first one now. This is the point, right? That's the point. And so this would be the length of that complex number, which is root 5. Now, how would we draw 2 minus I?
It would be negative 1.
Negative 1. Nice. And then this would be the point. But look at this now. Right here now. This line and this line have the same length. Even though this y value is negative, they have the same length, don't it? They have the same length. All right? Because minus 1 squared is just 1. So these 2 complex numbers have the same length. The only difference about them is one is located in what's known as the first quadrant, and this one is located in the 4th quadrant. All right? All All right, and this is useful for something else that we're going to be looking at very soon. All right, now let's look at C and D. So what's the modulus of part C of this complex number?
Would it be 5?
5, yeah, 3 square plus 4 square. 3 square plus 4 square. And so the modulus of that complex number is indeed 5. Very good. All right, the modulus is indeed 5. All right, now part D. Now part D, it says now we have cosine theta plus I sine theta. So now we want to find the modulus of this complex number. All right, so that'd be the modulus of this complex number. So this is your real part, your imaginary part.
Square root of cos squared plus sine squared.
Very good. The square root of cos squared plus sine squared. Now what's the square root of cos squared plus sine squared?
I don't know.
The square root of cos squared plus sine squared? What's cos squared plus sine squared?
I'm not sure.
So cos squared plus sine squared is 1. But we'll get to this when we look at trigonometry. Alright? We'll get to this part. Now it's good to know this identity from now that sine squared plus cos squared theta is equal to 1. Alright? Sine squared plus cos squared is equal to 1. When we do trigonometry, we look at the proof of why that is. So the length of this complex number is 1. So just to write it down, sine squared plus cos squared equal 1. Alright, because this identity is very popular in complex number. So we just need to write it down. Sine squared x plus cos squared x is equal to 1. Alright. Sine squared plus cos squared x, that's equal to 1. Or if it was theta, same difference. Alright, now also now, look at this now, some notes. These are just some stuff that we should know. The length of a complex number and the length of the conjugate of the complex number is the same. Alright, must remember this, the length of a complex number and the length of the conjugate of a complex number is the exact same. So for example, we looked at 2 plus I and 2 minus I. 2 minus I is the conjugate of 2 plus I, don't it?
Yes, sir.
Right? Yeah, and notice that their length were the same. So the length of the conjugate of a complex number is the same as the length of the complex number. All right. Now, the next thing to look at is what happens when you multiply a complex number times its conjugate. When you multiply a complex number times its conjugate, we looked at this last week, we said we get some real number. All right, well, that real number actually worked out to just be the length of the complex number square. So just to go back to last week of what we did, right? Just gonna go back quickly. When we multiplied two complex number, we multiplied the complex number and its conjugate. Going back last week, we worked it out and we got a squared plus b squared. Now a squared plus b squared is just the square of the real part plus the square of the imaginary part, right? And so what this really is, this is just the square. This is just the square of the length of the complex number. All right. Because remember again, mod z, in this case, mod z would just be the square root of a squared plus b squared. Mod z is just the square root of a squared plus b squared. And so what we're then saying is that z, a complex number z, times a complex number z star, right? When we multiply a complex number times its conjugate, the result that we're obtaining is actually just the modulus of a complex number squared. All right? So these are two popular results that we should know. All right, just two popular results that we should know with us. All right. Now, the next thing that we're going to talk about, you hear me keep on talking about angle. And the reason why I keep on talking about angle is because of what is known as argument. All right? Now, what is the argument of a complex number? The argument of a complex number, all right, is just the angle between the positive x-axis and the complex number itself. That angle is known as the argument of the complex number. All right? And if z is equal to x plus yi, then we say that the argument of the complex number theta is tan inverse of y over x. Generally, they don't call the argument theta. You're going to see arg z. Arg z is what they're going to call that angle. So let's look at a diagram just to get a pictorial representation of what we are saying. All right. So what we're saying then is, if we have an Argan diagram, right? This is an Argan diagram, and we have our real axis, and we have our imaginary axis up here. What we're saying is, all right, so let's say we have some complex number, 3 plus 4i. All right, 3 plus 4i. All right, so this is a complex number, and that's the point. All right, now what we're saying is this angle right here, this angle theta. Now this angle theta is known as the argument of z. And the argument of z is given as the angle between the complex number and the positive x-axis. So this angle is known as the argument of z. So this theta, they call that theta arg z. So theta is equal to arg z. All right, arg z, you're going to see this, arg z means the argument of z. All right, arg z, that's theta. Now, how do we go about finding theta? We use trigonometry. We're going to need to use trigonometry to find the argument of theta. All right, but the argument of theta is going to be different in each quadrant. All right, so first and foremost, let's look at the argument in the first quadrant. This one is for the first quadrant. This is a complex number in the first quadrant. All right, so this is argument in the first quadrant. Now, the argument in the first quadrant theta, like let's say just use a general representation. So this is x, and this is x, and this imaginary part is y. So this is a complex number x plus yi, right? To find the angle, how do you think we would find this angle? What's coming to your mind to how we could find this angle?
We can use the square root. We can square them.
All right, now this is where we're going to use rules from CSEC again. Trig ratios. So we're going to use trig ratios. So what's the tan of this angle? What's tan theta equal to? Tan theta.
Are you asking about like when we have the hypotenuse? And
Yes. Yes, so what would be the tan of an angle? Because this is a right angle triangle, and so we can apply trig ratios to find this angle. All right? And so the opposite is right here, where the opposite is a length of y.
So it'd be opposite over adjacent?
Yes, opposite over adjacent is tan theta, where the opposite is y and the adjacent is x. And so the tan of theta is y divided by x. And so to find theta, we just take tan inverse. So theta is just tan inverse y over x. Theta is just tan inverse y over x. And so that will give us theta, tan inverse y over x. All right? That would give us theta. So that is how we would find the argument for a complex number that is in the first quadrant. Theta is tan inverse y over x. All right? So that is to find the argument of a complex number in the first quadrant. Here it is, in the first quadrant. Argument in the first quadrant. All right, so let me give you an example. All right, so let me say, find the argument of the complex number C equal to, let's say, 8 plus 15i. That's in the first quadrant. So find the argument of this complex number. Z is equal to 8 plus 15i. Talk to me, how do we find the argument of this complex number?
So 8 would be on the real axis.
Yes, so if you were to sketch it, 8 is on the real axis.
And 15 is on the y-axis.
Yeah, the imaginary axis. So we have 8 on the real and 15 on the imaginary. All right, so tell me how we're going to find the argument now.
So it would be...
We're going to find the argument.
10. You'd use 10?
Yes, we'll use tan. Nice. So we use tan. So what would be theta? So theta is just going to be equal to tan inverse of what?
Tan inverse. Oh, it would be, where is it? Y. So it'd be 15 over 8?
Tan inverse 15 over 8. Very good. Nice. And that would be theta, tan inverse 15 over 8. What's tan inverse of 15 over 8? Put that in a calculator and let me know.
$61.93.
All right, 61.93. Let's just work with 61.9 degrees. And so that would be the argument of this complex number. And so after you find theta, you're not going to stop there. You're going to tell them that the argument of z, this just means the argument of the complex number is 61.9 degrees. Now, if they had asked you to put it in radians, you'd have to give them the answer in radians, but we just leave it in degrees for now. So that would be how we find the argument of this complex number that is in the first quadrant. Now, a complex number in the second quadrant is not going to have the same, it's not going to be the same method to find the argument. And let's look at why. If we have a complex number in the second quadrant, this is how the complex number looks. this is the second quadrant. So over here is the first quadrant. So this is the first quadrant. First quadrant. Second quadrant is over here. Second quadrant. Third quadrant is down here. Third quadrant. And right here is the fourth quadrant over here. Now to find the argument in each quadrant will be different. And now we're looking specifically to the second quadrant. Now what would be the argument of z in the second quadrant? How did we define argument?
Arguments?
Yeah. So we said that the argument is the angle between what?
Between, would it be x and y?
All right, so we said that the argument is the angle between the positive x-axis, meaning the positive real axis, and the complex number itself. So this is the argument. This is the positive x-axis. And so the angle between the positive x-axis and the complex number itself is the argument. So all of this angle is going to be the argument. So this is what I want to point out. The argument in the first quadrant, is always going to be between 0 and 90 degrees. All right, the argument is always going to be between 0 and 90 degrees. Can we see that?
Yes, sir.
Nice. So let's just write that down right here. In the first quadrant, we can clearly see that arc z is going to be between 0 and 90 degrees. So between 0, arc z is between 0 and 90 degrees, always in the first quadrant. All right? The argument of z is between 0 and 90 degrees in the first quadrant. Now in the second quadrant, what's the argument of z going to always be between? In the second quadrant, what's the angle going to always be between?
Would it be negative 90?
Not negative 90. So when we go from here...
Oh, is it going by like 90, 270, 180?
Yes, yes. Nice. So when you spin from here to here is 90, then from here to here is 100. So a complex number in the second quadrant will always be between 90 degrees and 180 degrees. All right, so here is 90 degrees. This is 90 degrees, this is 180. And so a complex number in the second quadrant will always be between 90 degrees and 180 degrees, always. Complex number in the second quadrant, the argument is always going to be between 90 and 180. So let's put that here. This is for the second quadrant. All right. So it's always between 90. The argument of z is always between 90 and 180. Always between 90 and 180. All right. And this is for the second quadrant. So let's just put it down here. So we're talking strictly for the second quadrant. Strictly for the second quadrant. This is for arguments in second quadrant. All right, so argument in the second quadrant is strictly between 90 and 180. All right, now how do you think we're going to find this angle now, all of this angle?
The one in the third quadrant?
In the second quadrant, how are we gonna find
half
all of
180?
Repeat?
Would it be half of 180? And then you add it with the 90?
Half of 180. They said 90 plus what?
So would it be half of 180?
All right. Now this is how we actually will do it. But good attempt. Now first and foremost, all of this is the angle, right? All of this is the angle, the argument of z. So all of this is theta. All right. Now what I'm going to do is I'm going to shade this part over here in red and this part of theta in blue. Now what's going to be the angle for the part in red? What's the sum of the angle part in red?
90.
90, very good. So only need to find the part in the blue. Now the angle that's going to be in blue right here, that angle that's going to be in blue, how can we find this angle in blue? Because this angle is not in the triangle, remember?
So wouldn't it be half of 180?
Why would this angle be half of 180? So to find this angle in the triangle, now think about it this way. If I were to put an x right here, x plus the angle in blue is going to be what? X plus the angle in blue will be what?
X plus the angle in blue?
Yeah, so this part, 90, right? X plus the part in blue will be 90, don't it?
Yes, sir.
Nice. But then now we can find this angle. We can find this angle right here by using trig ratios, don't it? We can find this angle x using trig ratios. So we can find the angle using trig ratios right here by saying that x is equal to whatever the length of this is for the x value and whatever the length is for this in the y value. Then we can say that, okay, in the second quadrant, x, I shouldn't use 2x here, can I use x as angle? And all right, let's call it a. Let's call it angle in here a. So to find the angle in here a, it's just going to be tan inverse of y over x. Tan inverse of y over x will give us the angle a, but then that angle we have to subtract it from 90 to get the blue angle. All right, and after we subtract it, so let's write down all of this now. What we're saying is that angle a right there, so is equal to tan inverse of y over x. A is equal to tan inverse of y over x. That would be angle A, don't it? Right?
Yes, sir.
Nice. Now look at this now. Now to find now all of the rest of this angle, right? All of this angle would just be 180 minus A. So the argument of z is just going to be simple as the argument of z is going to be equal to, I hope you're seeing what I'm saying, it's going to be all of this angle. So to find all of this angle would just be 180 minus this angle A. Can we see that?
Yes, sir.
Nice. And so what we say is that that argument is equal to pi. Now in radians, 180 is pi. So the argument of z is just pi minus tan inverse of y over x. Right? Pi minus tan inverse of y over x. That's how we find the argument in the second quadrant. Pi minus tan inverse of y over x. All right? Nice. Now, the same way we're going to do to find arguments in the third and the fourth quadrant. All right. Here are the summarized information. All right, because to take time and go through, break down all of them, it'll take a little while. But what I just want to focus primarily on is just remembering the formula to find the angle in each quadrant. So the first thing generally is when you're finding arguments, always put a calculator in radians, all right? Always put a calculator in radians. You know how to put a calculator in radians? Marika, you there?
Yes, sir. I'm checking.
All right, I can show you how to put the calculator in radians. So at the top of the calculator, you're going to see alpha and shift. You have alpha and shift on the top of the calculator. So in order to get your calculator in radians, the first thing that you actually want to do is press shift then alpha. After you press shift then alpha, you press mode and you press mode twice. After pressing mode twice, you're going to see degrees, radians, and grad. Degree is number 1, rad is 2, and grad is 3. All right. And then you press 2 for rad and your calculator is in radians. All right. Let me see if I can show you right here. So right here is your calculator. And so what you're going to do is you're going to say, okay, I want to put it in radians. The first thing you do is press shift. So I press shift. The second thing you do is press alpha. After you press shift and alpha, you're going to press mode. So you press mode, you see these come up, compute and some other stuff. That's not what you want. So you're going to press mode again. When you press mode again, then you see what you need, where it says degrees, radians, and grad. You want your calculator in radians. So you're going to press 2. Now when you press 2, notice the little small sign on the calculator. Change from a D to a R, because now your calculator is in radians. So for example, now the sine of 30 is a half, and the sine of 45. All right, so now when you put in other values, you won't get the answers in degrees. You're going to get them now in radians. So let's say, for example, tan inverse of, let me see, tan inverse of maybe 0.5. You're not necessarily going to get the same answer when you put it in degrees. So for example, tan 67. When you put it in radians, you're going to get different values, all right? And that is because we're going to then, when we do trigonometry, we're going to look at converting from radians to degrees. What we're going to learn is that 1 radian, which is what they call pi. Let's go to pi radians first. Pi radians is 180 degrees. 2 pi radians is 360 degrees. So those are equivalent. And so everything that we compute with radians and degrees are going to be different. All right. But for arguments now, we need to keep our calculator in radians. All right. All right. All right. So these are just some important information about arguments that we need to know. Arguments is measured in radians. Arguments is measured in the positive real axis. The principal argument is always between minus pi and pi. So what that means is that the argument is going to be between negative 180 degrees and 180 degrees. Also, if the complex number is in the first quadrant, theta is tan inverse of y over x. In the second quadrant, the angle is pi plus tan inverse of y over x. In the third quadrant, it is minus pi plus tan inverse of y over x. And in the fourth quadrant, it is tan inverse of y over x. So all that they're saying right here is when we have some complex number, when it's in the first quadrant and we want to find the argument, when we want to find the argument theta, we use this formula when it's in the first quadrant. First quadrant, we use tan inverse y over x. So the complex number in the first quadrant, we use tan inverse y over x, where y is just the imaginary value and x is just the real value. Now in the second quadrant, what they're saying is, this is the second quadrant, all right? And so in the second quadrant, to find the argument of the complex number, the argument of the complex number that we want to find is just pi plus tan inverse of y over x, all right? So to find all of this, it's just pi plus tan inverse of y over x. All of this is going to be the argument in the second quadrant. All right, so that corresponds to this formula. In the third quadrant now, we have a complex number that goes something like this. All right, so this is a complex number. It's always the angle between the positive x-axis. So we want the angle between the positive x-axis. So look how we're going to find this now. This is the complex. This is the argument that we want. We want the angle between the positive x-axis and the complex number. All right. Now notice this was the positive x-axis and this is the complex number. So because we want the angle between the positive x-axis and the complex number, this is the argument theta. The argument theta is then going to be equal to minus pi plus tan inverse of y over x. So let's look at these examples and we're going to see the difference. All right, so it says find, oh, these lists missing out. Find the argument should be here. Find the argument of the following complex numbers. Find the arguments. All right, so how are we going to find the arguments of these complex numbers? Let's start with A. Let's find the angle for part A. How are we going to find the argument of this complex number in part A?
We would use the first or fourth quadrant.
Yes, so it's in the first quadrant. So 1 plus I, if you were to sketch this on some Argan diagram, let's make a very small Argan diagram. Then this is 1 and this is 1. And so it's in the first quadrant. This is a complex number in the first quadrant, right? And so the angle that we want is this right here, all right? That angle that we want right there, all right? So let's call it theta or argument of z. You can call the argument of z theta if you want. Just write on the paper, argument z is equal to theta. So you can just write this on the paper, rz equal theta. And the reason why you have to write arg z is equal to theta is so when you're carrying out calculations where you're saying theta is equal to tan inverse of whatever, they're going to wonder where that theta comes from. You're just telling them that theta is the argument of the complex number z. So in this case, the argument of the complex number z is equal to tan inverse y over x. What's tan inverse y over x in this case? For part A, what's tan inverse y over x? What's your,
45.
all right, nice. So tan inverse y over x is tan inverse 1 over 1. And as you rightfully said, tan inverse of 1 is 45. Now 45 is in degrees, and they always want it in radians. All right, so 45 degrees in radians is pi by 4. So it would be pi by 4. All right, pi by 4. Now let's look at how I converted it to pi by 4. Now, the thing with radians is, I'm just going to show, we're going to get specifically into it when we look at trigonometry. So I'm just going to show you the shortcut to remember it. The shortcut that I use to remember it is always just write down this. Pi equal 180. Pi radians equal 180 degrees. So pi radians equal 180 degrees. So how am I going to get 45? To get 45, I have to divide 180 by 4. And anything I do to one side, I do to the other. So 180 divided by 4 gives me my 45. And so what I'm saying then is that pi by 4 is 45 degrees. All right. Now let's say in your calculator you got 90 degrees. What would be 90 degrees in radians?
Would it be 90 over 4?
90 degrees in radians?
So it'd be divided by 4?
Not really. So always start with this line. Pi is equal to 180 degrees. Always start with this. So if pi is equal to 180 degrees and I want to get 90 degrees, I'm going to ask myself, what number do I divide 180 by to get 90? What number do I divide by 180 to get 90?
2.
Repeat.
You divide by 2.
2, yes, very good. So I divide by 2. Now when I divide 180 by 2, what I do to one side, I do to the other. So what I'm saying is 180 divided by 2, 90 degrees is known as pi by 2 in radians. Pi divided by 2 in radians. Good. Now let's say I ask you for 60 degrees. What's 60 degrees in radians?
You divide it by 3.
Very good.
So pi by 3.
Yes, pi by 3 is 60 degrees in radians. Good. All right, and don't worry, we're going to get a lot more into it when we're looking at trigonometry. But for now, we're looking at complex numbers. So that's why I don't want to spend too much time looking at how we convert to radians. We'll go in depth in that in trigonometry. So now right here we have 1 minus I. What's going to be the argument of this complex number 1 minus I? Where's 1 minus I located?
1 is on a positive x, which is the real. So 1 is on the real, and negative 1 would be on the imaginary. So it would be the fourth quadrant.
Very good. This is 1 minus I. All right, so this is 1, and this is minus 1. So how do we find the angle in the fourth quadrant? We'll find the angle in the fourth quadrant.
It would be tan inverse negative 1 over 1, which would
Very
be negative
good.
pi by 4.
How you get negative pi by 4?
It's negative 1 over 1. So tan inverse negative 1 over 1.
Oh, okay, yes. Negative 1 and that, yes. So as you're saying, this is the angle which is negative pi by 4. Very good. Negative pi over 4. Because your y is negative 1. Very good. All right. All right, how do you find the angle now in the, for -1 plus I?
So that would be negative on the real and positive on the
All right, so we're in the
imaginary.
second quadrant. So when we're in the second quadrant, what's going to be the angle?
So it'd be 180 plus tan inverse 1 over -1.
Very good. So it's 180 or pi plus tan inverse of negative of 1 divided by -1. So you're still finding tan inverse of -1. So what's the answer now? What's pi plus tan inverse of -1? Now this is how you add them. Tan inverse of -1 you get. What we get for tan inverse -1?
Negative pi by 4.
We get negative pi by 4, so it is pi minus pi by 4. Now pi minus pi by 4, put it as one answer. This pi right here, I can rewrite pi as 4 pi divided by 4. Would you agree with me there?
Yes, sir.
And so 4 pi minus pi by 4 is just 3 pi by 4. 3 pi divided by 4. All right? And so that would be the argument for minus I plus 1. All right? Now what would be the argument of -1 minus I?
It would be in the third quadrant.
The third quadrant, very good. How do you find the angle in the third quadrant?
Negative pi plus tan inverse -1 over -1.
All right, so it's tan inverse of -1 over -1, which is tan inverse of 1, don't it? Taking tan inverse of -1 over 1, -1 over 1 just forms +1. And we said that tan inverse of 1 is what? What's tan inverse of 1?
Pi by 4.
Pi by 4. So we have negative pi plus pi by 4. Negative pi plus pi by 4. Now negative pi plus pi by 4, all right? Now we can always write negative pi as negative 4 pi over 4. Negative 4 pi over 4. You agree with this?
Yes, sir. So it would be negative 3 over 4 pi.
Very good. Beautiful. Negative 3 pi over 4. Negative 3 pi over 4. All right? And that pretty much takes care of argument. Negative 3 pi over 4. Beautiful. All right. Nice. Wonderful. All right. Now the next thing that we're going to be looking at now is what's known as trigonometric or polar form of a complex number. And let's look at how did they come up with this now. So right here, I didn't really get clear of where this formula come from. And so let's look at it somewhere separate. Let's go to somewhere cleaner. Let's look at where did all of that come from. Well, that came from, let's just picture a complex number in our minds first. So we have our y-axis, and we have our x-axis, and our x-axis is the real part, and our y-axis, as we know, is the imaginary part. So let's say we have the complex number in this color right here. All right, and let's say this complex number is, z is equal to x plus yi. So that's the standard complex number. Z is equal to x plus yi. All right, and so the angle between the real axis, the angle between the positive real axis and the angle between the imaginary axis is the argument of the complex number. And so the argument of the complex number, let's just call it theta. And so this is theta, right? That's theta, right?
Yes, sir.
Nice. Now look at this now. What would be the length right here? What would be this length from right here to right here? What's this length? This is just the imaginary part. What's the length of the imaginary part right here?
Would be y.
Would be y. And what would be the length of the real part all the way over here?
X.
X. Nice. Very good. Now look at this now. Using trig ratios, what would be the value of sine theta? What would be sine theta from this diagram? What would be sine theta? Remember, we call the modulus of this line, or the length of this line, r. So the length of a complex...
the r squared is equal to, so that's x squared plus y squared.
All right, that's for r. But now, what would be sine theta now? So looking at this triangle, how would we find sine theta? How do we find sine theta from this triangle?
We wouldn't use tan, right?
No, I'm asking you for sine, not tan. We're not looking at tan now, just sine theta. We're just looking at sine theta. How do we find sine theta? The value for sine of the theta. Remember SOHCAHTOA?
It'd be y over r.
Y over r, very good. Y over r, because it's opposite over hypotenuse. And so if we wanted to make y the subject, we're going to realize that y is equal to r sine theta. Can you see that?
Yes, sir.
So y is r sine theta. Now look at this now. Y is r sine theta. And if we were to say, okay, let's do the same for x. Now what would be the value for the cosine of theta?
Sir, is it okay if I take a 5-minute break?
All right. So you ready now?
Yes, sir.
Right. All right. As we were saying now, what would be the value of cosine theta?
So it would be r over x.
Cosine theta. What's cosine theta? Cosine theta is adjacent over hypotenuse. So what's cosine theta?
Adjacent, so also adjacent is y.
Adjacent is x. This is adjacent.
This is x over r.
X over r. Yeah, nice. So the cosine of theta is x over r. Now, since the cosine of theta is x over r, if we were to make x the subject, we would get that x is equal to, what would be x? Now, cosine theta is x over r. What would be x if we make x the subject? X would be r cos theta, don't it?
Yes, sir.
If we make x the subject, we get x is r cosine theta. So since x is r cosine theta and y is r sine theta, now look at this, voila. Now the complex number, we said that z is equal to x plus yi. Z is equal to x plus yi, right? That's a complex number, right? Complex number z is x plus yi, but we just found that x is r cosine theta, so we can write that x is r cosine theta, and then we just found that y is r sine theta, and so then yi becomes r sine theta times I, r sine theta times I. Now, since we now know what is x and y in terms of theta, what we can do is factor out r, since r is in common of these two, and so we get that if we factorize out r, we're getting cosine theta plus I sine theta, cosine theta plus I sine theta. And so any complex number can be written in Cartesian form, which is x plus yi, or we can rewrite it in this form, where it is the modulus or the length of the complex number times the cosine of the argument plus I sine the argument. Now this is known as the polar form of a complex number. All right, so this is known as the polar form of a complex number. Polar form. All right, so that's the polar form of a complex number. Very important, very, very, very important. Majority of complex number marks usually come on polar forms and exponential forms. All right, so this is polar form of a complex number. And you're good with how we got this, right?
Yes, sir.
Nice.
It looks similar to trig.
Yeah.
Yeah.
Yes, because this is, they call it trigonometric form or polar form. Very similar. All right, so that's where I had the sine theta is y over r from. The cosine theta is x over r. And so we made x and y the subject, substitute x and y into this formula to get z is r times the cosine of theta plus I times the sine of theta. And so we say that this is the trigonometric or polar form of the complex number. All right. And so to represent a complex number in polar form, we must find the modulus, which is r, and the argument. All right. And that's all we need to do to find a complex number in polar form. So here are some examples that we're going to do. So write the following in polar form. So to write in polar form, we just need to remember that the polar form of a complex number z is equal to r times cos theta plus I sine theta. R times the cosine of theta plus I sine theta. That's all we need to remember. Z is equal to cosine theta plus I sine theta. So all we need to do is find r and theta, and then we get it in its polar form. So let's look at number 1. So looking at number 1, how do we find r? What is r equal to?
So it would be -2 is on the real section.
All right.
Then I is on the positive. So it would be r is equal to
R is equal to the square root
Negative 2.
r is equal to the square root of minus 2 squared plus
Minus 2
1.
squared plus 1 squared.
Yes, minus 2 squared plus 1 squared. And so we get that r is equal to the square root of 5. All right, so that's going to be r. R is going to be equal to the square root of 5. R is the square root of 5. Now, let's find now theta. How are we going to find theta? How are we going to find the argument theta?
So we're going to put it in the cos theta plus sine theta form?
Yes, but before we do that, we need to find out the value for theta. So I'm saying, how do we find the value for theta? How do we find the argument?
Oh, it's the tan. So it would be pi plus tan inverse y over x.
All right, so minus 2 plus I, as we know, is in the second quadrant. So as you rightfully said, it is pi plus tan inverse of y over x. So it is pi plus tan inverse of what is y and what is x.
Y is 1 and x is negative 2.
All right, so it is tan inverse of negative 1 over tan inverse of 1 over negative 2. What's tan inverse of 1 over negative 2?
Negative 0.46.
That's what you get in radians?
Yes.
We're getting negative 0 point what?
46.
All right, very good. Now all you need to do is add that to pi. So you're going to add pi plus negative 0.46. And then what you get when you add them together?
2.67, 2.68.
All right, so let's leave it there. Good. Always leave it in 3 significant figures, 2.68, and that's in radians. All right, so now that we find theta and we find the modulus and we find r, then what we're going to say now is z is equal to r, and r in this case is the square root of 5. We're going to write the square root of 5 bracket cos theta, which is just the cosine of 2.68 plus I sine. So it's a cosine of 2.68 plus I sine the cosine of 2.68. And that is in its polar form or trigonometric form. Any way how you want to call it. I sine 2.68. All right. I sine 2.68. We good?
Yes, sir.
All right. Now let's look at one more before we move on. So I want to do, let's look at the second one. Or let's go to the fourth one. The fourth one, it looks a little bit different. So this says z is equal to 1 plus cos theta plus I sine theta. Let's write that in its polar form. So this is not in polar form, you know. All right. Z is 1 plus cos theta. So 1 plus cos theta. Then we have, so I want you to know for homework, do number 2, and number 3. When I send the notes, ignore number 4 for now, because when I think about it, we don't do trigonometry yet. So I really can't look at cos square plus sine square yet, and angle for 2 cos theta and cos 2 theta, and we don't look at those yet. So when we get to trigonometry, you'll be able to do more of these trig type of complex number questions. So we'll get back to that one. Well, maybe we won't get back to it, but when we're doing past paper questions and we finish trigonometry, you'll be able to tackle these ones. So no worries. All right, now the next part that we're going to look at is known as the exponential form. I can't show you the proof for the exponential form because we're going to have to do module 2 first, and that's using Taylor series and Maclaurin series, how to expand functions, how we write out sine x as a function of x. All right, we're going to learn what sine x is, e to the x is, all of these sort of stuff. All right, and we're going to do that when we look at Maclaurin and Taylor series. That's in module 2. So I can't show you the proof for this one. So just take it as a gospel for now that a complex number can be written in the form z is equal to re to the I times theta. This is the exponential form. Z is equal to re to the I times theta. This is exponential form. All right, this is the exponential form. So z is equal to re to the I theta, and it's the same as r cos theta plus I sine theta. All right, so for the first one right here, where we found that z is minus 2 plus I, and we found r and we found theta, what we're pretty much saying is that for the first one, we could go ahead and say then that z in exponential form is equal to r, which is root 5. Z is equal to root 5 e to the I times theta. E to the I times theta, and theta is 2.68 in radians. So it is e to the 2.68 I. And that would be it in its exponential form. All right? Z is equal to root 5 e to the 2.68 I. All right?
Yes, sir.
All right, no worries, you're going to get one to try. Let's try the second one in exponential form. So it would be r for number 2.
It would be r is equal to its root
The square root, yeah, of
they have to put it back like negative 2 squared plus 1 squared.
Oh, we're looking at number 2, not number 1, number 2.
Oh, negative 1 squared.
Yeah, negative 1 square.
Plus negative 1 square.
What's negative 1 square plus negative 1 square? All right, so negative 1. Yes, so that's the root of 2. Very good. That's just the root of 2. Now that we get the root of 2, then what we get now is we need to find theta. What's going to be theta?
It would be the third quadrant, negative pi plus tan inverse.
Very good. Negative
1 over -1.
Very good. So negative pi plus tan inverse of negative 1 over negative 1. So -1 over -1 is +1. And so what we're finding in reality is tan inverse of 1. So what's tan inverse of 1?
Pi by 4.
Pi by 4. So what we have is -pi plus pi by 4. So -pi plus pi by 4, we can always...
-3 over 4 pi.
Very good. So -3 pi by 4. That's the answer. -3 pi by 4. Let me write this 3 a lot better. So we get -3 pi by 4. -3 pi by 4. All right. So now what's z when we write it in complex, in its exponential form now? What's z?
Z would be root 2 cos -3 pi over 4 plus I sine -3 pi over 4.
All right, now that would be polar form, but the exponential form would be r e to the I theta. So for exponential form, it would be root 2 times e to the -3 pi by 4 I. All right? And that's the exponential form. In the polar form would be, as you were saying, root 2 times cosine of -3 pi by 4 plus I sine pi by 4. So you've already find it in polar form. So you could even just put it somewhere up here. That z is equal to everything that you just said. So now we only need to do number 3 for homework to find in polar form. So that would be how you write it in exponential form. All right. Now we're going to get to the nicest thing with complex numbers now. All right, complex numbers. And that is learning the Marvelous Theorem. Again, I cannot show you the proof of it because we don't do proof by induction as yet. That's when we're going to do that soon. When we look at mathematical proofs, and we haven't done trigonometry yet, so I can't show you the direct proof either. So you're just going to have to take this as gospel for now. So the Marvelous Theorem states that r cos theta plus I sine theta raised to the nth power is equal to r to the n times cosine n theta plus I sine n theta. All right, and so what this means is r cos theta plus I sine theta, as you know, this can be replaced by z, and this z is just x plus yi. So we're saying whenever we have a complex number raised to the power n, it's equal to the same as raising the modulus of the complex number to the n and multiplying it by cos n theta plus I sine n theta. So for example, what we're pretty much telling you with the Marvelous Theorem is, if I tell you I have maybe 5 in bracket cosine of theta, and let's say theta is pi, 5 times cos pi plus I sine pi, all right, and it is raised to the 3rd power. We can use the Marvelous Theorem, and instead of raising everything to the 5th power, expanding this out by the 5th power, what the Marvelous Theorem tells us is that if we have 5 times cosine pi plus I sine pi raised to the 5th power, the Marvelous Theorem tells us that it is the same as r to the n. In this case, our r is 5 and our n is 5, so it would be r to the n, r to the n, so it's 5 to the 5 times cosine n theta, so then it would be cosine, it would become cosine of n theta, theta is pi, n is 5, so n theta is 5 pi plus I sine 5 pi plus I sine 5 pi. Plus I sine 5 pi. All right? I sine 5 pi. All right, so that's the Marvelous Theorem. So R cos theta plus I sine theta to the n is equal to R to the n times the cosine of n theta plus I sine n theta. All right?
So n would be what r is?
So in this case, n is 5 in this case. But let's say it was a case where n was 4. If n was 4, let's say n was 4 in this case. If n was 4, then what we would get is r is 5, so it would be 5 to the 4. So in this case, the answer would be 5 to the 4. In that case, it would be 5 to the 4. 5 to the 4 times the cosine of n pi. So it would then be 4 pi right here. Plus I sine 4 pi. All right, so that's all the Marvelous Theorem is stating. All right, so all the Marvelous Theorem tell us is that if we have r times cosine theta plus I sine theta raised to the n, we don't need to go expand out all of this bracket. All right, him just simply provide us that the result is going to be r to the n times cosine n theta plus I sine n theta. The Marvelous simplified for us already. All right. So in this example right here, all we realize in this example right here, our r is 5. In this particular example, our r is 5. In this example, our r is 5, our n is 4, and our theta is pi in this particular example. So if it makes it easier, just always write down what your r is, what your n is, and what your pi is, so you can just follow this formula, right? So let's say, for example, I tell you to simplify for me what is 3 times the sine of, let's say, pi by 2, 3 sine pi by 2, 3 sine pi by 2, plus I sine pi by 2. 3 sine pi by 2 plus I sine pi by 2. And all of that is raised to the, let's say, the 8th power. So 3 sine pi by 2 plus I sine pi by 2, we're going to raise all of this to the 8th power. All right, so everything in this bracket is being raised to the 8th power. What would be the simplified answer for this if all of this is raised to the 8th power? What would be the answer?
Would it be 3 to the
3 to the
8th?
yeah.
Then sine
Times 3 to the 8th power times
sine
sine the sine of
pi by 2.
sine of pi by 2. You sure?
Oh no, it'd be 8
8.
pi
Yeah.
by 2.
8 pi by 2, and 8 pi by 2 is just 4 pi. Very good. 8 times pi by 2, which is just 4 pi. Yeah, continue.
Plus sine.
Plus.
Sine.
Oh, I start with, oh, sorry. This should have been cos. Yeah, it should have started with cos. It's cos theta plus I. Yeah, this should have been cos. Sorry. So it should have been cos 4 pi plus, continue, plus
Sine. I sine.
yeah, I sine.
4 pi.
Yes, I sine 4 pi. Very good. This is going to be very useful when we're doing calculations. All right? Because in reality, it would take forever to expand and work this out. So say they ask you to find the value of 3 times sine pi by 2 plus I sine plus I, oh, this should have been cos, sorry. No wonder I wrote sine over there. That part should have been cos. So say they give you a question and say to simplify 3 times the cosine of pi by 2 plus I sine pi by 2 to the 8th power. That's difficult to simplify. But using the Marvelous Theorem, we could tell them that is 3 to the 8th times cos 4 pi plus I sine 4 pi. The sine of 4 pi is 0. And then cos 4 pi, you put that in a calculator. And you say, oh, cos of 4 pi, you get 1. And so the answer works out to be 3 to the 8 times 1, which is 3 to the 8. So when we finish work all of this out, it's just going to be 3 to the 8th power, which is 6,561. So you see how easy we get to work this out? Just by knowing the Marvelous Theorem. All right? So all of this works out to be equal to 6,561. 6,561. You get the same answer as what I did?
Yes, sir.
Nice. And the reason why it is this is because we know that the sine of 4 pi is 0. I times 0 is 0. Cos 4 pi is 1. So the answer is 3 to the 8 times 1 plus 0. And so that's 3 to the 8 times 1. And it gives us that answer. That's how we will use the Marvelous Theorem. Now, right here, we cannot do the first 2 parts as yet because we don't know trigonometry. But when we do trigs, we'll come back to the first 2 parts. But this is a typical exam question, part 3. It says evaluate cosine pi plus I sine pi by 4 to the 8 using the Marvelous Theorem. Now talk to me. How are we going to do that? What does the Marvelous Theorem tell us? How are we going to work this out? Cosine pi by 4 plus I sine pi by 4 to the 8th power.
So
Yeah, go ahead. Tell me what to do.
so it would be
It's gonna be
8.
8.
Can you scroll up so I can look back at the
Okay, the theorem. All right,
yeah.
no problem. So let me zoom it out a little bit. So here's the theorem. So in this
Okay.
case, what is R?
So R would be nothing.
R would be 1, not nothing. R is 1 in this case.
Okay.
So think of this as 1 times all of that. All right. So expand it now for me. What would be the answer?
So it'd be 1,
Yeah?
then to the 8th power,
Yeah. 1 to the 8th. Yeah.
then cos pi by
Bracket.
4.
Cos.
Cos pi by 4.
Cos pi by 4. You sure? Look at what this says. It's a cos n pi, n theta.
N theta.
Mm-hmm.
Oh, so it'd be pi by 4 times 8
Very good. Pi by 4 times 8. So 8 pi by 4
would be
which would
2
just be
pi
2 pi. Yeah. So it would be
plus
1 to the 8 plus cos 2 pi plus
sine I sine 2 pi.
I sine 2 pi. Beautiful. I sine 2 pi. I sine 2 pi. Very good. Now we can actually work out what this value is. We can actually work it out now. Because what is cos 2 pi? Put it in a calculator. Cos 2 pi. So you're getting 1 to the 8 is 1 times what's cos 2 pi? Cos 2 pi? Cos 2 pi?
It'd be 1.
Cos 2 pi is 1, indeed. Cos 2 pi is 1. Plus, what is now I sine 2 pi? Put in a calculator sine 2 pi.
Zero.
All right, very good. So it's 1 plus 1 times 0. 1 plus 0. And so it works out to be just
2.
1. 1.
Oh, sorry. I made a mistake. 1.
Yeah, so it just works out to be 1. All right, nice. So it works out to just be 1. Beautiful. It works out to just be 1. All right. So that's our answer. So imagine this. Normally to find this answer, what we'd have to do is to just expand all of this to the 8th power, don't it? We'd have to write down this times, this times, this times, this times, this times, this times, this 8 times, don't it? But the Marvelous Theorem gives us an easy way to find this. All right. Now, all right, I like this one too. It says find the value of 1 plus I to the 10th power. So let's do that one together. Find the value of 1 plus I to the 10th power. How do you think we're going to do that? Find the value of 1 plus I to the 10th power. How are we going to do this? 1 plus I to the 10th power.
So it would be 1 to the 10th power.
You sure? Now, before we can do that, the first thing we need to do is rewrite 1 plus I in polar form. So what I want you to do is rewrite 1 plus I in polar form. So if I have a complex number, let's say Z1, and this complex number is 1 plus I, this is 1 plus I can find what R is. What's going to be R?
It's gonna be 1.
R is going to be 1. What's
Sorry.
R?
Would it be the square root?
The square root of?
Of 1 squared plus 1 squared.
Very good. So it works out to be the square root of 2. Then what's going to be theta?
It's going to be tan inverse 1.
Tan inverse of 1, and tan inverse of 1 is pi by 4, right?
Yes, sir.
So we get that theta is pi by 4. Very good. So now we can rewrite the complex number 1 plus I as now this part right here in the bracket. Look what I'm going to do. I'm going to write that all of this is working out to be in this bracket 1 plus I can be written as root 2 times, it can be written as root 2 times cosine pi by 4 plus I sine pi by 4, right?
Yes, sir.
So it's root 2 cosine pi by 4 plus I sine pi by 4. So now that we can rewrite it in this form as root 2 cosine pi by 4 plus I sine pi by 4, now we're nice, because now we rewrite 1 plus I in this form. Now all we need to do now is just raise all of this to the 10th power. Now that we raise all of this to the 10th power, we can use the Marvelous Theorem. So what's this going to work out to be now?
So it's gonna be root 2
Root 2
to the 10th power.
Beautiful. Root 2 to the 10th power. Root 2 to the 10th power. Yeah.
And then cos pi by 4 times 10.
So it's going to be root 2 to the 10th power times cosine of pi by 4 times 10. So that's the cosine of 10 pi by 4. Cosine of 10 pi by 4. I want to simplify it. That looks like 10 pi by 4. That's 2.5 pi. Yeah. Then what else?
And I sine 10 pi by 4.
Plus I sine 10 pi by 4. Very good. I sine 10 pi by 4. So what I want you to do now is tell me what is root 2 to the 10th power. What's root 2 to the 10th power?
32.
Root 2 to, very good, 32. So it's 32 times, what's cosine 10 pi by 4? So when you're putting that in a calculator, work out what it's 10 pi first, then divide that by 4, and then put the cosine of that value. So that your calculator don't get confused. All right? So what's cosine 10 pi by 4?
Would it be 2?
All right, so let me show you how you put
Do mixed fractions don't count, right?
All right, so I'm going to show you the easy way to put in a calculator. So right here you have your calculator. You're going to say, okay, pi. So you're going to say 10, that's 10. Then you put your pi, 10 pi. So here's my 10 pi. 10 pi, you find what that answer is. Then you're going to divide it by 4. So that answer, you divide it by 4. So this is 10 pi divided by 4. After you get 10 pi divided by 4, you're going to take the cosine of this answer. So all right, now the cosine of the result, cosine of 10 pi by 4, here it is, that's 0. All right, so that's how you put it in the calculator. All right. So that's good. That's good.
Yes, sir.
So work out what is sine 10 pi by 4 for me now. So this is 0 plus work out the sine of 10 pi by 4.
1.
1. Very good. So this becomes I times 1. I times 1 is just 1I. And so the final answer just works out to be 0 plus I is I. I times 32 is 32I. So all of that up there can be simplified to just be 32I. All right? 32I. That's good?
Yes, sir.
Very good. Nice. So that answer is 32I. So this works out to be 32I. Now that we get that the result is 32I, so let's write that down. The result is 32I. All right. That's the result, 32I. All right. Now we're almost finished. So we're going to do complex number in 3 weeks. Next week, we're just going to do a worksheet of complex number. Today, we're just going to finish going through the topics, all right, or the contents. So now the next thing to look at with complex number is what is known as locus. All right, locus. Now what is locus? Now consider this. Let z be equal to x plus I times y. And let p be some point. All right, p some point xy, which has a complex number that's just the same z. So p is the point representing z. Now the locus of the set of point P is the set in which the complex plane satisfies a given condition. So locus is just, the locus of the point P is just the set of points that in the complex plane satisfies a given condition. For example, let's say C is an element of complex numbers and R is an element of real numbers. If they tell you that the locus of Z satisfying the condition, so let's say they give you this, the modulus of Z minus C equal R. What they're telling you is that this is a circle with center C and a radius of R. So for example, they might ask you to describe the locus of this. Z minus, they put in bracket, it says Z minus 1, 8. Really? All right, let's say they give you, let's say they give you Z minus in bracket 1 plus I, 1 plus I, close bracket, and that's equal to 3. What they're telling you is if they give you this locus, they're telling you that this locus is a circle. This is a circle with center, C, and your C is 1 plus I. Now 1 plus I as a point, that would be 1, 1. So they're telling you this is a circle with center 1, 1 and a radius of 3. All right? So that's just the form that you have to study. So you have to study this right here, is to study what this form means. If you see Z minus C, this C here is just a complex number. And remember, complex number is in the form A plus BI. All right? So let's look at an example. For example, it says describe and sketch the locus of z, where z is -1 minus I, and it's equal to √2. So what is this saying?
So it's saying that the center is -1, and the radius is √2.
Ah, you almost get it. You're 90% right. So this is what it is saying. First and foremost, z, this is now right here, you want it in the form z minus c, right? Z minus c. This is not in the form z minus c. To get it in the form z minus c, right here what we're going to have to do is we're going to have to do some factorization. So right here we're going to have to write z minus, and we're going to factor out. So z minus in bracket, this becomes 1 plus I. Can you see how I get the 1 plus I?
Yes, sir. You factor out the negative, so then when it times it, you get -1.
Very good. So you have to rewrite it in that form, all right? So you have to write it in the form z minus a. And so the center in actuality is 1, 1, and the radius is √2. All right? But you were definitely on the right path. All right? And so that would be the locus. So now to sketch the diagram now, the diagram is going to be looking like this. Oh, I didn't sketch the diagram. So let's sketch the diagram for ourselves. All right? So to sketch this diagram, we would just draw a circle. Let's draw our circle. This is my y-axis, x-axis, top center 1, 1. I'm just drawing my circle. Move it up. How do I move it up? Oh, no, I know how to move it. So let's say this is the circle. And let's say here's the center now, 1, 1. So the center is 1, 1. So with the center being 1, 1, that's the center. And all you'd have to do is put on that the radius is √2. All right, the radius is √2. So you just draw a line R, and that radius R is √2. All right, and that would be the circle. Only thing left to do is put on your imaginary axis, which is IM, and your real axis RE. Your real axis RE. All right. I'm gonna have to get a mouse until my finger recover, because this is not working at all. So recently, just to state what happened with my finger. Recently, a lot of pus started to came in one of my fingers, and I went to the doctor recently, and it's discovered that in my finger I have paresthesia, and I'll have to take antibiotics for the treatment to reduce the swelling and all of that stuff. So it makes me write really poor these days, and it's just difficult to even feel any movement in my finger. So when I touch it, I don't really feel it. My finger, it's numb. But when I squeeze the area, it really hurts when I squeeze it. All right, so that's why.
Did they tell you how you got it? Did they tell you how you got it?
Well, there are many. The doctor was saying there are many causes. It could be something like excess water. My hand has been in excess water. He also said it could have been something about the nail extending and growing too deep inside of the skin. whole heap of different reasons, but he gave me lots of antibiotics and stuff. And he said usually in 2 to 6 weeks my finger will be better. So this is still week one. Week one ends tomorrow, so I'm just hoping right now. So yeah, my writing will be bad for a little bit. So I'm gonna try to get a mouse so that I can write better. At least with the mouse I get support and I won't have to be using the cursor. All right. So that's why this week the writing has been so off. These things happen. All right. So that's the locus for this now. So tell me what would be the locus. What is this one now? It says describe and sketch this locus. Tell me what this locus is telling you.
So it's saying do we have to factorize it as well?
Yes, always put it in the form z minus a.
So it would be z minus positive 2.
Yeah.
Minus 1 minus I.
Yeah.
Is equal to 1.
Very good. And that's equal to 1. So then what is that? What is this telling you?
That the coordinates is 2, -1.
All right, so always write first, it's a circle with center 2. It's a circle with center 2, -1. And what's the radius?
1.
And the radius 1. Very good. All right, what's the second one saying now?
So the second one would be z minus -2 -4.
Very
I
good. -2 -4i
is equal to 2.
Yeah, that's good. And that's equal
And
to
then
2. So it's
circle
a
with center
circle with center
-2 -4.
-2 -4.
And the radius is 2.
And the radius is 2. Very good. And radius 2. Very good. Very, very, very good. Nice. All right. Very good. All right. Now, the next thing that we're looking at, the next type of locus is what is known as a perpendicular bisector. All right. Generally, this is the most popular one that comes, the one with the circle. So I can show you some Cape paper. I'll show you a Cape paper right now. And I can show you a Cape paper and you're going to see that this is the one that they always pretty much come. On the paper too. But on the paper one, sometimes they put the others. So it's good to know all of them. Now what they're saying now is A is a complex number and B is a complex number. The locus of Z satisfying this condition, the modulus of Z minus A is equal to the modulus of Z minus B. That locus is a perpendicular bisector connecting the line from A to B. So for example, let's say describe and sketch the locus of Z that satisfies the condition Z minus 1 plus I equal Z minus 1 minus I. First thing, put it in its standard form. We can rewrite this as Z minus in bracket 1 minus I, comma, and that's equal to, simplifying that part, it's Z minus in bracket 1 plus I. And so what we actually get in reality is that this is saying that the locus is a perpendicular bisector, connecting, it's a perpendicular bisector joining A to B. This is A. So it is joining, it says a perpendicular bisector joining A, and A has coordinates 1, -1, 1, -1, 2, 1, 1. All right. And that's that one. All right. So it's just the locus is a perpendicular bisector joining 1, -1 to 1, 1. So if we were to ask to sketch it on a graph, what that means is we have our imaginary and our real axis. Now this point 1, -1, the real part is 1, the imaginary part is -1. So this is our point. Let's call that A, 1, -1. Then we have a point 1, 1 is B. This is 1, 1. 1, 1 is B. All right. So so this is the line 1, 1. All right, let me do it in blue. All right. So what it is telling us is that we have some line that looks like this. And then the locus is just the perpendicular bisector of a line that is joining A to B. All right. And that would be the perpendicular bisector that is joining A to B. All right. And that's it. Now let's look at the second one, and you're going to describe for me what this one is saying. What is this locus saying?
Z -2
Z minus 2
plus 2i
plus 2i, yeah.
is equal to Z
yeah.
minus I.
Z minus I.
Z minus I.
You sure Z minus I? What are you saying? Z minus I?
Yes.
Okay, that sounds better, which is actually 0 minus I. All right, and there's a reason why I put the 0, because the real value for this part is 0. All right, so what is this locus saying?
Saying that the locus is a perpendicular bisector joining 2, 2 to 0, -1.
Bisector joining, what you say? 2, 2?
2, 2 to 0, -1.
Very good, beautiful, beautiful, beautiful. Nice, that is indeed the locus. Nice. All right, nice. Now there are two more types of locus that we're gonna have to know. The next one is half line. So if A is a complex number again, and theta is the angle measured in radians, then the locus of Z that satisfies this condition, the arg of Z minus A equal theta. This is a half line starting at the complex number A that it is making with the positive real axis. So for example, it says describe and sketch the locus of Z minus 1 minus I equal pi by 4. Put it in its standard form, Z minus A equal pi by 4. So what this is saying is that this is the locus, is a half line starting at 1, 1, making an angle of pi by 4 with the real axis. All right? And that's half line. So let's try this one now. Describe and sketch the locus of Z where the argument of Z plus 1 plus I is 3 pi by 4. So tell me what this is saying. What's this one saying?
So it's saying z minus
All right, very
-1.
good. So we're saying the argument, always right about the argument of z minus z minus
-1,
yeah,
-I.
negative I. Cool, good. And that is 3 pi by 4. And you know that that is 3 pi by 4. So what is this locus telling us?
The locus z is a half line starting at -1, -1, and making an angle of 3 pi by 4 radians with the real axis.
Very good, very good. The locus is a half line with starting point -1, -1, and the angle of 3 pi by 4 with the positive real axis, and an angle of 3 pi by 4 with the positive real axis. 3 pi by 4 with a positive real axis. Three pi by 4 with positive real axis. Very good. All right. Nice. That's what we have for the locus. All right. All right. So good now. So there's a final type of locus now. And the final type is the straight line locus. So whenever you get now z is equal to a plus lambda times b, where a is a complex number and b is a complex number, the locus of z is a line passing through a that is parallel to b. So it is a line passing through a that is parallel to b. So for example, describe and sketch a locus of z, where z is equal to 1 plus I plus lambda times 2i. So the locus of z is a line passing through 1, 1 that is parallel to 2 minus 1. All right, so describe this locus for me. It says, describe and sketch the locus of z, where z is -1 plus 2i plus lambda times 3 plus 4i. What's that telling us? Describe that
Locus
locus.
of z is a line passing through -1, 2, and parallel 3, 4.
Very good. So the locus of z is a line passing through, what's the point it's passing through?
-1, 2.
-1, 2,
And parallel 3, 4.
and is parallel to 3, 4. Very good. Now if they ask you to sketch it, I'm going to show you how to sketch it now. Now to sketch this locus is pretty different. It's not going to be like sketching the others. All right, it's a little bit different. So let's look at how would we sketch it. They've never asked to sketch it, that's why I didn't put any diagram. Well, let's look at how you typically sketch it. So you start with your real axis, your imaginary axis, your real axis. All right, the locus of z passes through -1, 2. So -1, 2, I'm going to use R for real, RE for real axis, and IM for imaginary. It's my imaginary axis. Ouch. So, all right, so I'll leave it there. And so minus 1, 2 now. Minus 1 is over here and 2 is up here. So let's say this is the point minus 1, 2. Minus 1, 2. If this is the point minus 1, 2, then we're good. All right, now it passes, the locus passes through this point and is parallel to 3, 4. Now this is going to be 3, 4. 3, 4 is, let's say 3 is here and 4 is right here. Let's say right here is 4. Then this is the locus of 3, 4. All right, that's 3, 4. And so if we were to draw the line that represents 3, 4, this is the line that represents 3, 4, don't it? This is the line that represents 3, 4, don't it? Right?
Yes, sir.
That's 3, 4. Now the locus of Z is going to be a line that passes through minus 1, 2 and is parallel to this line. So since it's parallel to this line, it passes through minus 1, 2 and it's parallel to that line. So this is the locus and it continues and go down and down and down. All right, go down and down and down. So let's stretch it. No. Let me see if I can stretch it. Yeah, it goes down and down and down and down and down and down and down. And up and up and up and up. The only thing that we know is that it is parallel to this and it passes through this point. They are parallel when their gradients are the same. All right? And that's it.